Hello, my name is Julie Pinchiaroli, and I'm a rising sophomore at Bucknell University. Our project focuses on the mechanical properties of F-actin and intermediate filaments composite networks. The cytoskeletons of eukaryotic cells play vital roles in cell motility and division by altering their components, actin, microtubules, and intermediate filaments. To carry out the experiment, we polymerize the two proteins separately, each with their own buffer. Once the filaments formed, we then mix the two into one tube very carefully along with microspheres, which are necessary for our use of the optical tweezers. As can be seen in the confocal microscopy images, the two subsystems nicely form composite networks at varying ratios. Using the optical tweezers, we can trap the microsphere in these networks and measure the mechanical properties. Once the sphere is trapped, we pull it against the network at a constant speed to measure the exerted force on the sphere. This is the strain phase. Then we hold the sphere in its position to measure the relaxation of the network as well, called the relaxation phase. We will first focus on the strain phase, and on the strain force graph, we can see that the sample containing only vimentin, which is the purple curve, has a very low force response, indicating that the network is more viscous than that composed only of actin, which is the black curve. Furthermore, I took the derivative of the force with respect to stage position in order to detect when the network stiffens and softens. As shown on the graph, the flat slope for the purple vimentin curve indicates that not much stiffening occurs in that network. From this, we found the maximum K value and the time at which it occurs. This tells us that the vimentin network tends to soften to a viscous regime quickly. Now we are looking at the relaxation phase, and as you can see on the relaxation force graph, the actin network sustained some force while the vimentin networks tended to fully relax to zero, further emphasizing the difference in viscosity of these proteins. By curve fitting to a triple exponential decay, we can see that there are three different mechanisms by which the network relaxes the induced force. Lastly, I took the average terminal relaxation force and noticed that the data grew exponentially, showing a low terminal force for the vimentin network, which indicates how viscous it is, and a high terminal force for the actin network, showing that it doesn't relax completely to zero. In conclusion, VIFs and F-actin proteins are thought to form separate coexisting networks, but we show that they form interpenetrating networks that enhance their mechanical responses. Networks with higher actin concentrations exhibit stronger and more sustained elastic force responses to induced stress, and higher concentrations of vimentin exhibit complete relaxation of induced force. Thank you for listening to my presentation.